Good morning. My name is Bill Carty. I was a professor at Alfred University for roughly 30 years. And I retired in 2020 and now live in New Hampshire. I'm a consultant for the industry. I also work for several companies. American Ceramic Society approached me a few months ago asking if I would do this technician introduction to ceramic materials. And that ended up with a technician's guide to ceramics. And so what I'm going to do today is I'm going to walk through a bunch of things. I'm going to share my screen. You are welcome to post questions as we progress. You can try to raise your hand. I may or may not see that, but I think we're in pretty good hands at the moment. And then the second thing would be you can drop questions into the chat. Okay. So what I'm going to do is share my screen, and that should work perfectly. And then after that, we are off to the races. Okay. So what you should see is this. Technician's Guide to Ceramics. Correct? And that should be clear. So in the course of teaching ceramic engineering at Alfred University, I have been fortunate to collect a lot of great samples, also to observe a lot of things regarding ceramics, and to say that I'm passionate about ceramics is accurate, I think. In these images on the front, the left hand side here is a femoral hip joint, basically an application of ceramics in a bio application. The center are silicon nitride ball bearings that go into windmills. Kyocera, somewhat iconic zirconia knife. These are great examples. And on the far right, we have a dingware. It's a Song Dynasty vase, or vase, if you wish. It's in the was in the Percival David Foundation collection in London, is now in the British Museum. If you get a chance to see it, you should see it. It's remarkable. What I like about it is the spiral cracking in the neck. Still a bit of a mystery as to why. The picture here to the left of that is a typical porcelain body on the left and a glaze on the right. And there's a crack in the glaze. In fact, a crack such as this one here. But in cross-section, you see that the crack stops at the body. This is an image of clay particles. You see a 1 micron size bar, and here's a sintered aluminum microstructure. Just great examples of ceramics. Okay. Now, as an introduction, posted on the Dropbox, as well as the presentations from today, tomorrow, and Thursday, is a glossary of common ceramic engineering terms. And so this says 2009. It probably could stand a little bit of updating, but not much. Most of these terms were adopted by the ASTM C21 committee and are now in the ASTM standards from C21 committee. ASTM is a good resource for you. If nothing else, it's a great resource for standard testing methods. Okay. CO8 is refractory, C21 is whitewares and glass, and C28 is advanced ceramics, and there are several other committees that generate standards. All of these standards are published within 2 volumes, 1501 and 1502. PowerPoint presentations are presented or are posted to the Dropbox. If you go to the Dropbox now, you'll see this presentation. And then, as it says, with and without annotation, here's annotation, because what I can do is annotate on the screen. Okay, so you will get both copies of those presentations when we get done. And your questions are welcome. So our focus today is to differentiate ceramics from other material science and materials, metals and polymers in particular, to answer sort of the question of what are ceramics, what are their chemistry, how are they made, what are they made of, the material properties that make ceramics unique and thus of great industrial benefit, as well as other things. And then I'm going to spend quite a bit of time on mechanical properties of ceramics and specifically of brittle materials. And the focus of this discussion about mechanical properties is because, to be honest, there's a lot of folklore in the ceramic industry that attributes properties and behavior sometimes to the wrong thing. So in the course of our research over the past 30 years, we have developed a hypothesis, if you will, that manufacturing processes generate a series of defects. Now, that's not to say that they are wrong or a problem, but what we found is that materials produced within the same factory tend to have the same defects. And while we don't have a lot of data points to support this, we have some pretty nice data that argues this is true. So if I look at ceramics and materials in general, so I have metals, polymers, and composites. When I was in grad school, a friend of mine was a metallurgist, excuse me, and I used to say that metallurgy is a fad, that he should have gotten into ceramics. Okay, so metals in general, they're composed of metallic elements. We'll talk about that in a minute. They have metallic bonding, meaning that they share electrons freely, a delocalized electron cloud. And that delocalized electron cloud makes them very good electrical and thermal conductors. They tend to be opaque. They often have a luster, and they're strong, and they deform under load. Okay, they can deform elastically or plastically. Elastic being that if you bend a coat hanger, for example, and then you don't bend it too far, it goes back to its original shape. If you bend it too far, it now plastically deforms and you have a permanent deformation. Those are metals. Polymers, typically hydrocarbons, sometimes other non-metallic elements, boron, carbon, in addition to carbon, boron, silicon, etc. These often have very large molecular structures and covalent bonding. Electrically and thermally insulators, low density and low thermal stability, and low strength, but often very flexible. I mean, the extreme being, say, a rubber band compared to, say, a plastic bottle, for example. Okay. Composites are interesting, and a lot more interest in composites in recent years, particularly with emphasis on the design of high-performance materials. These are engineered structures, so their properties are tailored for the application. So the best example is fiberglass, for example. Fiberglass is a glass fiber that's embedded in a polymer matrix. And in that situation, the glass fiber carries most of the load, but the polymer matrix provides some flexibility to that. These structures, they're heterogeneous, and they're highly oriented based on, in other words, their anisotropic properties are highly dependent upon the orientation of the fibers. A lot of interest also in generating fiber reinforced composites for high performance applications. But in general, these materials are at the moment mostly low temperature. There are some examples of high temperature materials, but these are composites. So to get to the composite part of it, you would really have to understand the polymer part of it, maybe the metal part of it, but certainly the ceramics. So when we get to the more interesting stuff, being ceramics, of course, these are compounds. With the exception of carbon or graphite, which is listed down here under carbides, and in a different font style because it's a stretch to call it a carbide, I suppose. These are all compounds composed of two elements at least, a metallic and a non-metallic element, okay? To which we usually refer to them as cations as the metallic and anion as the non-metallic. So these typically have ionic bonding. We'll talk just a little bit about that later. Means they have very strong bonds. They are not so much sharing electrons as stealing electrons. So oxygen will readily take an electron from magnesium, for example, 2 electrons. Okay, they are electrical insulators or semiconductors. They're good thermal insulators. Typically, they have an intermediate density, intermediate between metals and plastics. They have great thermal stability, very high melting points. They're typically very strong and hard, but brittle. Okay, so we're going to discuss brittle failure specifically in a few minutes. So at the bottom, you see examples. We have oxides, which are by far the most common. Okay, so oxides, anything we do with this, it includes glass, by the way. So aluminum oxide is probably the most common oxide that you're aware of. Silica, for example, SiO2. This can be crystalline as in quartz, or it can be amorphous as a glass. Zirconia is famous. If we add a little bit of yttria to this, we get a stabilized, partially stabilized zirconia, which resists crack propagation. So we have then accomplished toughness or less brittle behavior. So oxides comprise probably the vast majority of the manufactured ceramics today, but that is likely changing with time. And probably changing in time towards carbides. So silicon carbide is the most common. Silicon carbide is used for a number of things that you're probably aware of. Sandpaper, grinding wheels, for example. The same with aluminum oxide also, by the way, but silicon carbide is probably our most famous abrasive material and being used for a lot of other things now. Semiconductors, your white LED lights, blue LED lights are silicon carbide, basically. Tungsten carbide is an extremely strong, extremely high temperature stable material used for cutting tools. Boron carbide, another carbide material. There's a whole host of them. And then carbon and graphite, carbon and diamond also fall into this category. Okay, and diamond being the hardest material on the planet, and graphite, those are all examples of carbides. Nitrides, silicon nitride is common. I mentioned silicon nitride ball bearings in the first slide, and silicon nitride ball bearings are used in windmills in particular. Aluminum nitride is unique, almost unique among ceramic materials in that it has a high thermal conductivity, but is a good electrical insulator. And the only other material that behaves that way is beryllium oxide, which beryllium has some issues with toxicity that make it undesirable. And then we get into boron nitride, and boron nitride comes in many forms. One is it looks like graphite, so it's a lubricant. And one it looks like diamond, where it's a super abrasive. So these are nitride materials, okay? And then at the bottom, I have borides. Borides are becoming more interesting because they have some interesting properties. You'll notice I put boron nitride in there twice. One under nitrides, one under borides. Titanium diboride is the coating you see on gold-colored drill bits, for example. And so these are all of our ceramic materials in terms of chemistry, okay? Oxides, carbides, nitrides, and borides. In a very high elevation view, there are two general classifications for ceramic materials and all minerals for that matter, but ceramic materials in particular. We're either crystalline, meaning we have long-range periodic order, where the same atom repeats in its location in the structure over and over and over again. Okay, so most of the materials that we work with in ceramics are polycrystalline or crystalline. So if they're crystalline, then they have the crystal structure, long-range order. Polycrystalline means that we have centered together or stuck together a bunch of small crystals or crystallites to form that material. So regular periodic array. Amorphous materials have a random network, no long-range order, no repeat units, as it were. And that structure is the structure of glasses. We call it amorphous, and we call them glasses. And they offer us a much different melting behavior, much different material properties overall in general, but they still exhibit the things that we like and don't like about ceramics. They tend to be high strength. They tend to be brittle, which we typically don't like. The other thing is, though, that they can have almost an unlimited range of compositions. So that gives us a lot of flexibility. These are just two cartoon images that I pulled out of the internet somewhere that show the differences. But this random long-range order, what we find in ceramics a lot of times is that this random, no long-range order structure is in between grains in a sintered microstructure. So almost all of our ceramics have often some amount of amorphous material. So to give you sort of a context of this, I deleted van der Waals from my list here, and because I think that's more or less important for us in general. Metallic bonding, delocalized electrons, this electron cloud argument, non-directional, great electrical thermal conductivity in common metals. Covalent bonding means that that bonding energies between two atoms are similar, and therefore they share electrons, creating highly directional bonding, but they're typically not stealing the electron from one atom to another or one element to another. Polymers tend to be covalently bonded. Gases are like nitrogen, for example. Carbon is covalently bonded, such as diamond, silicon carbide. Okay, so carbon carbides are often covalently bonded. So you have diamond here. Okay, you have silicon carbide. Those are covalently bonded, and then they fall into the heading of the non-oxide ceramics. The same with silicon nitride. Ionic bonding, which is most common in oxides, we have a large electronegativity difference. And what that means is that one atom will steal the electron from another one, okay? And interestingly enough, the one that it steals from is very happy to give up that electron. But what that does is it creates a very strong bond, okay? And the lattices that we generate typically are relatively isotropic in that these bonds tend not to be directional because it's essentially stealing an electron from another. The consequence of ionic bonding is very strong bonds, high melting points. These materials have very high melting points, but also because the electrons are strongly held by those ions in that structure, you have low thermal conductivity and low electrical conductivity. And this is where we are with ceramics, okay? If you're not familiar with the periodic table, as I say, greatest invention in probably the history of mankind in some respects. And the way that this works in general, if you are not familiar with it, is that properties in the column direction are similar. So the first column is the fluxes: lithium, sodium, potassium, rubidium, cesium. Second column is also the fluxes, and here is beryllium, magnesium, calcium, strontium, and barium. And then in this center section, we have the transition metals here. And then these are called the representative elements over here. And the last column is a noble gas. That's a pretty rapid view of the periodic table. But what you have is similar properties up and down in the column. And then properties are progressive as we move across the table. Okay. Why am I telling you all this? What we have in ceramics, and by the way, to use a table, the number in the upper right in this table, 20, is the number of protons in the nucleus. The 40.08 here is the atomic mass of that element, an internationally agreed upon symbol, and the name of it in English, in our case, okay? And then this 2 tells me that calcium will give up 2 electrons readily. Why do you care about that? Because if it gives up 2 electrons, calcium becomes calcium 2 plus, okay? And when it gives up 2 electrons, it gives them up to oxygen, so you would get CaO, for example. So oxygen, which is 2 minus, because it wants to take 2 electrons, plus calcium gives you CaO. Why do you care about that? You care about that because that is why alumina, Al2O3, is Al2O3, because aluminum over here is 3 plus. And oxygen over here is 2 minus. And if you want to get into that in more detail, I'm happy to discuss it. But essentially, by where these elements fall on the periodic table tells us how we get this chemistry. Okay. So, for example, a further example, sodium would be Na2 plus. Na2O, excuse me. because sodium will give up 1 electron, but oxygen wants 2, so it takes 2 sodiums to satisfy that oxygen. Down in the bottom here, we have the lanthanides and actinides. These are rare earths, and if you pay attention to the news, these are really of interest right now because they're very hard to get. And down here at the bottom, we have our nuclear materials, our radioactive materials. This chart I developed because I teach ceramic science for artists, and the symbols that you see here are not symbols that you typically see on a periodic table. The red square with the black dot, such as here for silicon, indicates that these elements as oxides would like to form glass, an amorphous random structure. The yellow squares with the blue squares in between are fluxes. They help to melt that and break that silicon network. And then we have intermediates, etc., such as, well, alumina is one, but titanium is one, for example, beryllium, where they go into the lattice in a different way into the glass. Anyway, this was designed to help artists understand better how the periodic table works. For making ceramics, however, what we are doing is we will take, say, oxygen is the easiest one to start with. We'll take oxygen and we'll combine it with something else. Let's say we combine it with zirconia. So you would see here that this is 4 plus or plus 4. Okay. And oxygen is 2 minus. And so when I combine these together, I get ZrO2. There's my oxide. So over here, these are anions, and these are the metals, cations. But also, just to keep things confusing and to make sure that I always have a job, we have silica plus oxygen here, so you get SiO2. Here's aluminum here, there's Al2O3. Okay, so these are the oxides. For carbides, they're then bonding carbon with metal ion. I have nitrogen bonding with a metal ion, for example, to form nitrides, or with silicon, etc. So we are combining 2 elements from different sides of the periodic table, basically, to form ceramics. And that is through ionic bond formation. So, by the way, for artists, they really like the transition metals because that's how we get color. Chrome, for example, highly colored. Copper can be red or green. Nickel is brown. Zinc is white, not particularly important. Cobalt, bright blue. Okay, so that's where metal ions come into play for artists. So to give you a more global perspective, okay, composition of the Earth's crust was measured many years ago. My recollection is in the 40s, but I may have that wrong. And what they did was they collected samples from many places on the planet's surface, primarily of shale. You say, why shale? Because shale represents a material which is typically a sedimentary deposit. So it represents the rocks that it came from, and then is metamorphosized by pressure into, it's essentially a clay metamorphized into a planar or flat material called shale. But analyzing all these materials, why I'm showing you this is that in the Earth's crust, you can see that oxygen is by far the largest. Nearly half of the content of all of the minerals in the Earth's crust, nearly half, is oxygen. In the ocean, it's 85%, and that makes sense if you think of H2O just simply, right? How much oxygen do you have in H2O, where hydrogen is 2 and oxygen is, hydrogen is 1, but there's 2 of them, and oxygen is 16, okay? But the fact is you have a lot of oxygen in the ocean also. You don't care about that so much. Silicon, though, in the Earth's crust is a lot of that. So this gives us then SiO2, which we occasionally find in the Earth's crust as SiO2, but it also shows up in all other materials. Feldspar, so for example, quartz, clay, other things such as granites, micas, etc. They all have silica, and then we have aluminum. So you see that at this point, right, in the system, we are roughly 72%, something like that, of the Earth's crust. Maybe, is that right? I think so. No, 82% of the Earth's crust made up of oxygen, silicon, aluminum. Aluminum also shows up in clay. It shows up in feldspar. It shows up in shales. It shows up in montmorillonites, etc. It rarely shows up in a form that we like it for making aluminum products. In that case, it shows up as bauxite. A very small percentage of this is bauxite. Okay. Iron is next, calcium, sodium, potassium, magnesium, and titanium. And after that, we're into the noise. So the Earth's crust is by and large made up of roughly 10 elements or 9 elements. The rest is in the noise. You notice here, you don't see silver, gold, mercury, uranium, whatever. They're an extremely small portion of the Earth's crust. Hydrogen shows up in the Earth's crust, typically in clays. Phosphorus shows up rarely, also in clays, but in some other minerals. Calcium phosphate, for example, which is mined for fertilizer and other things. And so you get an idea of what the Earth's crust is made of. In other words, everything that we get out of the ground is typically an oxide. And there is a few exceptions. Okay, everything in the Earth's crust is basically oxide. The exceptions are occasionally we run into sulfides. And the sulfides are combined with things like copper, for example. So when I have copper, okay, and copper in the Earth's crust gives me copper sulfate, or sulfide, excuse me, then that's beneficiated to get copper. So you can imagine then, also based on the amount of sulfur in the Earth's crust, that these are very rare. And so they are very valuable because we need the copper. And there's another number of other sulfides, but they're rarely available. Silicates, feldspars, quartz, clay, etc., are highly available. They're everywhere, which is part of the reason why ceramics came into being in the first place. Okay. So properties of ceramics versus other materials, typically very high melting points. Okay. Now I can give you a simple example, which is a little bit trivial, but it is my best example. Aluminum metal melts at about 620 degrees C. Aluminum oxide melts at about 2050 degrees C. Okay. Well, that's the best example because if I go to silicon metal melts at 1414, but silica melts at 1723. Okay, so that's not as good an example, but aluminum is my best example. Metals tend to have lower melting points, highly variable. Highest melting point material on the periodic table is tungsten metal, somewhere north of 2600 C, I think. Okay. Ceramics tend to be good electrical insulators and good thermal insulators. They can be optically transparent. So you can see glasses, of course, are transparent, but many oxides are also transparent if they're processed properly. Okay. They tend to have very high strength and stiffness. And stiffness, this is also called elastic modulus. And we will come back to that. They tend to be brittle. So we're going to spend a lot of time talking about brittle behavior, but essentially brittle behavior is that once a crack starts to propagate in that material, there's nothing to stop it. So the crack then will speed through the material. Typically the velocity of the crack is the speed of sound in the material. And so there is no mechanisms, no intrinsic atomic bonding type mechanisms or microstructural mechanisms for the most part in these materials that can absorb that crack energy and slow that crack down. So if you were in high school, for example, and someone dropped a plate in the cafeteria, you could be sitting across the room and not even see the event. But when it hits the floor, you can hear from the noise whether it broke or didn't break. And what you're hearing is the speed of sound in material if it broke. The ceramics tend to be abrasion resistant. Okay. and they tend to have low thermal expansion coefficient. Now, to give you a better understanding of ceramics compared to other materials, I'm bringing in Ashby diagrams. They were developed in the late 50s, early 60s by a guy named Ashby, actually published a couple of books. They're really quite useful, but what they do is they compare fundamental properties, and I just selected a few of them to show you so that you can see where materials then show up within this spectrum of what's available today. And interestingly, those diagrams are now a bit outdated because we've been developing more materials that have higher temperature applications, but allows you to see how these materials behave and to evaluate, if you will, material properties. Now, there's an interesting thing about this is that for ceramics, the properties are dictated by the microstructure, okay? So, and that is in turn dictated by the processing. How we process the powders to make the ceramics dictates our microstructure. And so things such as elastic modulus, E, is a property. But technically speaking, strength, represented by sigma, is not a property because this is a function of microstructure. Okay, I'll say it's microstructure. And so this strength is not a property. And so if my processing is poor, my strength is poor. If my processing is excellent, my strength goes up. Okay, so we have a bit of gray area, if you will. So the first place to look, in my opinion, is to look at density, which is down here, okay, on the horizontal axis or the x-axis, versus Young's modulus or elastic modulus on the y-axis. Now, you need to pay close attention to these scales. This is 0.1, and this is 1.0, and this is 10. So this is a logarithmic scale. Now, I like this scale a lot because it shows me that if I do something like 1, 3, 10, 30, 100, these are equally spaced on a logarithmic scale. So that may be very useful for us later on if we design experiments to keep this idea in mind. Okay. Young's modulus, though, is similarly done on a log scale. And so the logical question that you might ask yourself is, well, why show these things on a logarithmic scale? Why not do 1, 2, 3, 4, 5? Because our properties change by orders of magnitude. So that means that I can have very flexible materials, such as polymers, which have an extremely low elastic modulus, or I can have extremely stiff materials, such as engineered ceramics with a very high elastic modulus. And so the consequence is, if I did it on a linear scale, you would see the ceramics in that scale, but all of the polymers would be in the noise at the bottom of the scale and be indecipherable. So we have a number of things to point out, okay? This range up here, which I'll crosshatch for us, these are engineering alloys. And then if you get into the books, he'll tell you what is this one here, you know, and what are these materials up here, etc. Okay. First thing that you should see is that if I look at this just from a general perspective, these are typically pretty high densities, from 3 up to about 20 grams per cubic centimeter. Okay. Engineering ceramics are here. Okay. And engineered ceramics are high elastic modulus, but typically a narrow range of density and lower density in the system than metals. I get into engineering composites over here. Here's my engineering composites, basically. Okay. And then the brown ones here are wood, but notice they have very low densities. And of course, if the density is below 1.0, then they float in water. Okay. And then you can have a highly oriented material. This is parallel to the grain. This is perpendicular to the grain. And you see that there is about an order of magnitude difference in stiffness if I am parallel to the grain or if I am perpendicular to the grain. Polymers, by comparison, they all sit down here. Okay. Polymer foams are here. Here are engineered polymers. Okay. What you should notice in this figure is that my engineered polymers have a maximum elastic modulus somewhere around 10 gigapascals, and my ceramics have a minimum elastic modulus of somewhere close to 200, 150 or so. Engineering alloys sort of span that difference a little bit, starting somewhere around 20, okay, here, 20 gigapascals, up to about probably about 400 gigapascals. So if you are looking at something which has a need for low mass, so say an aircraft component, you might choose to, but you need high stiffness, you might go to an engineered ceramics. What's the trade-off? Well, the trade-off is that the high performance ceramics tend to be brittle, meaning that they don't resist crack propagation. So they fail catastrophically. And that's the whole game here and the plan of what we're trying to do. So that brings us then to the next, which is K1C. So this is called a fracture toughness, okay? And K1C means that it is the resistance to crack propagation in mode 1, so K1C, okay? And that 1 refers to tension, okay? So K1C, a higher K1C means a greater resistance to crack propagation. So now if we look at our materials again, he conveniently colored these things to all be the same, okay? Oh, I thought he did. Yeah, he did. So your reds are your metal alloys, your whatever color that is engineered ceramics, light blue, turquoise, something like that. So here's my engineered ceramics, okay? And their fracture toughness ranges from about 10 to about 2. Again, log scales. But notice that they are very high strength. So they're up to basically 10 gigapascals in strength, okay? And so that's 10,000 megapascals. So here, very high strength, but relatively low fracture toughness. Metals have extremely high fracture toughness, right? Or very high fracture toughness. So we like metals for applications where we expect the material will see a lot of flexing and movement. We loved it for aircraft skins, for example, because it stops crack propagation. Aluminum alloys fit into that picture. Here's your aluminum alloys in the middle of this figure, basically. And aluminum alloys were great for aircraft applications. Wood tends to be about the same fracture toughness as ceramics. Porous ceramics are down here, lower fracture toughness for porous ceramics. And then you get into your engineered polymers in here, which also have relatively poor fracture toughness and lower strengths. You said, well, why would you want to use that? Well, we tend to design things to be the maximum strength that we can manage. But the bottom line is that we don't always need that much strength. And so your polycarbonate in your eyeglasses, for example, you don't have to have particularly high strength, but you would like it to be low low mass. So there's a lot of opportunities. And so you design the material, or you select the material based on the design that you need. Okay. So if I come down to the next one and look at fracture toughness versus density, okay, this is density here. We designate with a rho versus fracture toughness, okay. Now your ceramics are low density, which is good for us. This is porous ceramics here, and here's my engineered ceramics. But my fracture toughness values are as we were before, but at a lower density range. So what do I give up when I go to engineering alloys? Well, I might be able to keep the same density range in my aluminum alloys and some of my titanium alloys, maybe similar in density to what I have with ceramics, but I get much better fracture toughness. Okay. And then lastly, and perhaps most importantly for us in terms of ceramics, is strength at temperature. Okay, so this is strength as a function of temperature here. Okay, so this is strength. Okay, So versus temperature. It is, again, not a linear scale, also a logarithmic scale for temperature. And this is K at the bottom, so you know that K minus 273 is C, degrees C. So at the top, I have temperature and up to 1400 degrees C here. What's happened in recent time is we have pushed this out, and we are pushing this out to the 2000 C range. So this eventually is going to come out something like this, and probably something more like this, where our strengths will suffer by increasing temperature because things start to move. Okay. So our engineered ceramics, though, have the best high temperature performance of any of the materials, which is great because that's what we wish to use them for, is high temperature applications. And so metals, depending on the aluminum alloys now, are very low temperature. They have very limited temperature ability. You know, you're down below roughly, here's 500 degrees C. Okay. I can't exceed 500 degrees C. And there's you can find a program on things like how do they make extruded alumina, and they just make it warm, and it super plastically deforms. Okay. When I was referring to making new materials out here, okay, basically what I get is here, this engineered, my engineered composites here, composites are going to be this for ceramics. Okay. They're going to be the ones that move out here. It won't be ceramics by itself, but it's going to be composites for the most part because of the fracture toughness issue. Okay. But you can see then the strength at temperature. So as our temperature goes up, in general, strengths go down. The overall trend here would suggest that as temperature goes up, strength goes up, but we are pretty seriously limiting our materials based on a temperature limitation. So polymers, elastomers, low temperature, maximum, relatively low strengths or very low strengths, 2 orders of magnitude below what you would see for ceramics. Our engineered polymers, they get better. Our composites then improve things above that. So you have then, here's our engineered composites, right? So what we have is we are tailoring the materials for the application temperature. So hopefully that gives you a visual of how these materials behave in terms of what the differences are between ceramics and metals, for example, which is our major competitor in most cases. So what you get is high melting points for ceramics. Okay, electrical insulators. I didn't give you a chart for electrical insulation, but we'll talk about that in a minute. They're electrical insulators. They are thermally insulating, and they are optically translucent, I say, rather than transparent. They can be transparent, but optically translucent. High strength and stiffness, right? But low toughness. And they're abrasion resistant, and they have low thermal expansion coefficients. So with this high melting point argument right here, okay, that leads us to an interesting situation, right? The need for ceramic processing. So the question is, why is it that I have to do powder processing? So I could put in here powder as an added term, need for ceramic powder processing. Because what I have is a brittle material. Okay. So a brittle material means that I can't take something like I take steel, and I can put it into a hammer mill, for example, or essentially a pneumatic hammer, and I can bang that steel into place because it plastically deforms to allow me to do that. If I do that with ceramics, I get nothing. I get powder back, right? The very high melting points eliminate the potential for melt forming. The only exception here, right, is, of course, glass. Okay, so we melt glass. What's interesting about glass, though, is that when it melts, its viscosity changes continuously with temperature. Okay, so if I were to illustrate that for you, for example, okay, so if I look at melting. Okay, what you typically see is that if you looked at, say, temperature versus elasticity, it would come across to be very, very elastic. It might have some small decrease in elasticity as it approaches the melting point. And when it hits the melting point, T sub m, it drops precipitously and becomes a fluid. Very, very low elasticity. A glass, by comparison, okay, and I'm going to use a different term here. I'll use viscosity, which we typically have an eta symbol versus temperature. Okay, the curve now does this. So as I go up in temperature, my viscosity changes, but it isn't this abrupt change. If I were to look at a metal, the problem with a metal is I can't really represent it as a viscosity, but you might imagine that it comes across like this, and then it hits T sub m, which we're going to define to be out here for sake of argument. Okay, and that T sub m in a glass is dictated by a specific viscosity, which is typically about 10 to the 1.5. Okay, but my metal would come across with a very, very high viscosity and then suddenly drop, right, to have a low viscosity at that point. This is a log scale, meaning that I might have 10 to the 20 here, okay, and then I might be 10 to the 10, 10 to the 5, etc. It's going to be a huge change in viscosity with temperature, but it's still very viscous. So there's this, I mentioned folklore before, and it's sort of the standard joke, right? In old buildings, you find that the windows in an old building, right, are typically thicker at the bottom, right? So you have a window in a building, you know, and the window is thicker at the bottom. And the question is, why is that the case? And the argument is, oh, the glass flows. And actually, it's not quite true. It's they put the thick end down. Okay, so this is false. The windows are thicker at the bottom, yes, but not because of viscous flow. So at temperature, oh, by the way, and if it was, all your skylights would be bowed in. Okay, so what you have is that there's a number of points in viscosity. If you go to the glossary, which I mentioned at the beginning, in the back of the glossary is a list of defined viscosity values for glass. But this is our glass here. And say, we have this continuous curve of viscosity. That allows us to do melt forming. Okay. So, and then as I change my composition, I can change then where this curve shows up, but the shape of the curve remains roughly constant. Okay, so if I change my flux levels in the glass or whatever, I can shift that curve around. If I want to make sheets of glass, such as in a float glass plant, this works for me because I melt the glass, I get it to be low viscosity. And then as I cool that, the viscosity goes up and I can work that glass with that viscosity curve to allow me to do things that I wouldn't be able to do otherwise. If you look at a glass blower, they'll take the piece that they're blowing, maybe it's a bottle or a vase or something, and they'll work it for a little while. And you probably don't notice it by standing by watching them, but it becomes too viscous for them to work. Then they go back in the furnace, they heat it back up again. It becomes more fluid. They bring it out, they'll blow on it, for example, they'll blow in it through a blowpipe, and it will expand, you know, as they are working with that viscosity. And what they're doing is they're moving on this diagram, okay, in different places. So they are moving basically, so for some, say here, okay, from this temperature to that temperature, this is what happens, okay. They bring it out of the glass blowing chamber and it's here, and then they put it back in, and then as they work it, the viscosity, the temperature goes down, viscosity goes up by several orders of magnitude, too viscous to work, they put it back in the furnace, and they keep cycling that, and they do that an infinite number of times. So glass allows us to do melt forming, nothing else. Ceramics, metals, such as, for example, aluminum oxide, okay, or aluminum oxide would behave like this. Copper metal would behave like this, but T sub M, of course, would change. So the need for processing is that we are then forced to work with powders. So we take the powders, they're typically small, and the powders are then combined in such a way that we like them to be individual particles, nicely stuck together. And of course, I drew these ideally as little spheres. We'd rather them to be uniformly distributed with nice uniform pores rather than a big open three-dimensional network of defects and large pores and clusters of particles that are difficult to eliminate, okay? So when I do this, I end up with a pore microstructure, potentially, because all this space then has to be eliminated during sintering versus this, which is more ideal, okay? So I have to understand how to control the powders in the manufacturing process to control the way that they consolidate. Slurry processing is superior as a way to do for body preparation for forming, but it's also expensive, okay? And so in that, I mean, it costs money to remove water, all right? So you have to slurry process, you have to eventually remove the water, okay? And that costs money. So other processes are direct forming processes where the powder goes into a mixer of some sort. And there's a variety of them available. And then you add water or some other liquid until you get a body which can be plastically formed. The processing defects limit the yields. They degrade the properties and the performance of the material and the components. So what is a processing defect? Okay, so a processing defect could be this. It could be in an otherwise good matrix, it could be a cluster of particles, okay, which does not break up in the process and retains itself as a cluster of particles, okay? This is called an agglomerate. Okay, and agglomerates are eventually become our defects in our ceramic matrix in our component that we produced, and we will come back to that for sure. All right, right here. This may be the most important statement of the day in some respects. There are no off-the-shelf ceramic components. Okay, what that means is that unlike steel, where you can go buy steel in a wide variety of shapes, angle irons, channel, I-beams, flat plate, cold rolled, hot rolled sheets of material, a variety of different compositions from tool steel to mild steel to stainless steel to et cetera, right? Work hardening steels, et cetera. They're all available off the shelf, and then you can take that material and machine it, okay? The high, I should add in here brittle, right, as the first point, okay? Brittle means that I also can't machine the material in order to, I can't make a slab of it and easily machine my component out of it. It costs a lot of money to do that, all right? So whereas I can go and buy a ready-made piece of steel for an application, or I can go buy a piece of pipe, for example, from the hardware store. There are very few ceramic materials that are off the shelf. If I want a ceramic component, I go to a company and I say, this is what I need. And then we'll negotiate over how much detail am I going to give you in terms of tolerances and requirements. And then you're going to determine if you're making that component for me, what it's going to cost. And as I make my restrictions, as I make my requirements more restrictive, my cost goes up. Okay. But every ceramic component, with few exceptions, is made for the application, is made to order. So years ago, I worked at Wisconsin Porcelain. They made fuse bodies, which are no longer used for the most part, but they also made a bunch of components, chicken coop heaters, for example, tumbling media, etc. All those things were made for the application. None of it was off the shelf. And that's still true today. So with that in mind, right, we start looking at properties, right? So I have, for example, let's start with thermal expansion coefficients down here, okay? So thermal expansion, I just pulled some things out of the literature. This website, if you were to Google coefficient of thermal expansion, you'll probably find this site, topsaco.com. I liked the illustration, which is why I picked it, okay? So on this curve, our thermal expansion coefficient, okay, which is the slope of this line. So this is temperature down here, and this is percent expansion, okay? So essentially, this is delta L over L times 100, okay, is my expansion. So what that means is that I put in a device that I have my sample in a device, and I have a probe that pushes against the sample, and it sits in this tray, and it gets heated, and it measures the change in dimension of that sample as a function of temperature. Okay, so there's a whole number of things here that are of interest. Polymers and nylon down here, a greater slope means a greater thermal expansion coefficient. So you can see it's a very high expansion coefficient. This is aluminum alloys here. The slopes of these lines are changing dramatically. Magnesium oxide is basically our highest thermal expansion coefficient ceramic. And I go down here, silicon carbide, which is on my chart here, silicon carbide is coming in somewhere around 3. MgO is around 13, which is not on my chart, but it would be approximately here. Okay. So it's a huge difference in those materials, but not as huge as it would be for aluminum, which fits way up here. So here's my aluminum alloy, okay? And then here is silicon carbide down here. Okay, so you get an idea. Lowest commonly produced material, fused silica, which is amorphous silica. Okay, and that has a thermal expansion coefficient of 0.5 times 10 to the minus 6 per degree Kelvin or per degree C. And that's this unit here, 10 to the minus 6 per degree C. Okay, so fused silica practically has no thermal expansion coefficient. There's another material called beta eucryptite, has a negative thermal expansion coefficient. It's a lithium aluminosilicate. It shows up in Corningware, for example, the blue flower, white casserole dishes. It has a negative thermal expansion coefficient. That's called a glass ceramic. So you have that crystal in a glass matrix, and the ratio of the glass to that crystal give the overall component a 0 thermal expansion coefficient, which gives us good thermal shock resistance. So it says boron nitride is negative. We have quartz, silicon nitride, aluminum nitride. Here is silicon carbide, silicon metal, tungsten metal, aluminum oxide, molybdenum, tantalum, niobium. Sapphire is aluminum oxide, but single crystal. Okay, and then zirconia. And then here are my metals, nickel, copper. I think this is a steel, silver, and aluminum. And these are also metals, but these are very high temperature metals. Niobium, tantalum, moly, and tungsten and silicon are high, are all metals. They have low thermal expansion coefficients. So by and large, you would say that the CTE of ceramics is less than the CTE of metals and much less than the CTE of polymers. Okay. How about thermal conductivity? Well, thermal conductivity is interesting, of course. Tungsten here, aluminum, copper, silver. Okay, so silver has very high thermal conductivity. Copper is next. These two are practically the same. Aluminum metal has good high thermal conductivity. Steel, which shows up down here, has low thermal conductivity. But here's your tantalum, niobium, etc. Boron nitride is in here. Silicon carbide has higher thermal conductivity. Aluminum nitride has high thermal conductivity, which makes it a good electronic packaging material because it's also an electrical resistor. And so what I have, though, why I show you this plot on the right, this goes to 20, okay, here. And here is 20 in my curve. So this is 100. Here is 20 in this plot. It's the other axis, right? But this is the maximum on my curve here. Log scale for thermal conductivity, same units, by the way, watts per meter K. And so what you see is that all of these materials are in this small area down here, okay, or this area, if you will, okay, in this plot. So, and then we've differentiated. Silicon carbide's at the top. Here's magnesite, alumina, mag chrome from a refractory, fire chrome, silica, and then fire clays. And down here, you get into insulating materials. Insulating fiber bricks are here are castables, and this is then fibrous materials, fiber refractories. So you see that all of these materials shown on this plot, this is refractories here, have thermal conductivities that are in the noise of this data. Okay, so everything else is going to be much higher thermal conductivity. These materials were actually designed to give us low thermal conductivity because we want to use them as insulators in furnaces, and they also benefit by having very high melting points. Okay, this is a duplicate slide, so I remove it. All right. So another material property is called a heat capacity. It's sort of an interesting, perhaps a little bit difficult to understand at times. It's how much heat is required to raise the temperature of a body. And so you have a specific heat capacity, which is then the heat capacity divided by the mass. Okay, so joules per K, that's joules per Kelvin. This is temperature. Okay, so the amount of energy necessary to raise something by 1 degree. So you can also have a volumetric heat capacity based on volume. But this is most common mass, this one, okay? So, and then we have British thermal units, for example, and you have calories on a gram basis, etc. And 1 calorie is roughly 4.2 joules. Why am I showing you this? Because it says, so if I need a small amount of heat to raise the temperature of something, it would have then low specific heat, right? And it would be a good thermal conductor. So I just have an example of some materials. We're going to ignore water for the moment, okay? So my concretes, terracotta, granite, graphite, and glass are all here, okay? And then they have a heat capacity that's roughly double or maybe even factor of 7 or 8 times the heat capacity of, lead, for example, is a very, very easy to heat material. Small amount of energy is required to increase the temperature. So lead, copper, iron, they're all, iron being an example of, it's almost exactly a factor of 2 before you get to glass, right? I bring water in here for a good reason. Notice water, right? Water is 4 times concrete. That means that it requires a lot of energy to increase the temperature of water. This makes our processing expensive. It's because in order to evaporate water, I have to put in a lot of energy. And so if I have to dry a ceramic component, I have to use a lot of energy in order to do that. But I will point out air, right? Air is interesting because as an insulator, if I incorporate air, air is a good insulator because it requires a lot of energy to increase temperature. It is, by the way, equivalent to concrete. So lastly, I have the energy cost to produce materials. Several years ago, I was working with Boston Valley Terracotta, and they were getting a lot of pushback on the amount of energy necessary to produce terracotta. And it comes from architects and what have you. Well, it's not a very environmentally friendly material. Turns out it's a very environmentally friendly material in terms of amount of energy per ton. Terracotta falls into this clay, brick, and tile range. It is the lowest energy requirement for any of the materials produced is terracotta. Cement is surprisingly low here, and glass is our most expensive. Plasterboard, okay, sheetrock, if you will. Why is this so expensive to produce from an energy perspective? Is because of water and the need to evaporate the water in the production. Water that's used outside of that necessary for chemical reactions has to be evaporated and it costs a lot of money. But by comparison, if I look at the other materials, my best case is glass to steel, which is 2x, right? But if I go up here to aluminum, it's a huge amount of energy required to produce aluminum. And it's because I have to do a carbothermal reduction or a the process by which I reduce aluminum oxide to aluminum metal is incredibly energy intensive. Copper, stainless steel, and plastics are surprisingly high because this requires the processing of petroleum. So ceramics actually, from an environmental standpoint, are excellent. And these numbers incorporate everything. They incorporate drying. They incorporate your process, of course, but the process energy is small, okay? Drying and then firing, okay? You could also say sintering or heat treatment, okay? These materials, ceramics, all of that energy for these process steps is included in these numbers, okay? So ceramics actually are energy efficient. So that brings me to the introduction of strength of materials and brittle failure. Would you like to take a 5-minute break, or are we good? You're welcome to ask questions either in the chat or you can try to raise your hand, and I think that we'll find you if you do. So let's launch into this. We have about 45 minutes left today, and I think I can get through mechanical properties and strength issues so that you have a better understanding of that, and then we'll set the stage for tomorrow. So essentially what we have are there's a strength issue. It's in brittle materials, there's a large discrepancy between the predicted strengths, the theoretical strengths, and the actual strengths that are measured. The other thing we find, and this is the big issue with ceramics, is that there's a lot of scatter in that data. You can have extremely high strengths and then occasionally a very low strength. And so there was a student a few years ago who had produced samples, and they had the lowest strengths I'd ever seen in ceramics. And I said I was quite impressed by that. I don't think the student appreciated my comment. But the problem with ceramics is that because of the way things are stressed, surface conditions become critical, because a defect at the surface then is in the highest condition of stress, and that's the one that will then propagate. We also find that larger specimens give us lower strength, okay? And in some cases, although it is rare, okay, this is rare, we may see that if we test things faster, our strengths go up. This is more true for glasses than for ceramics. And then if I go up in temperature, typically my strengths decrease. That's common. We mentioned bonding before, and in glasses and ceramics, this becomes important for us for strength. We have ionic or covalent or a mixture of the both, almost always a mixture. Ions, basically, they don't move very much, okay? There's Directional bonding is also relatively rare, except when you get into composites. Charge considerations, this mainly deals with something called cleavage, which is where you would fracture along a crystallographic orientation. Then they have to be a balanced charge to make that happen. But the biggest issue we have is this: microstructure dictates everything in terms of the strength of these materials for the most part. Okay, because if my microstructures are irregular, having big grains and small grains, for example, or pockets where there are no grains, where I have a hole, that increases the likelihood of failure or becoming what's called a critical flaw. And at room temperature, there's no viscous flow typically, no plastic deformation. Okay, so the consequence is everything is brittle. Okay, so what controls the strength? Flaws. It's actually that simple. Okay, flaws control the strength. What's a critical flaw? Well, a critical flaw is the flaw that dictates the strength. So if I have a specimen, okay, when I was a student, not really understanding this very well, I thought, well, can I calculate what my flaw size should be? And the thing is that your flaw size then, right, is dictated by your strength. So the strength then is a function of 1 over the size of the flaw. So as my flaw size increases, my strength goes down. C goes up, strength goes down. Okay. So if I have a specific strength level, say I'm 200 megapascals, I could calculate what the flaw size would be necessary. And I would have to stay below that flaw size to maintain 200 megapascals. I need elastic modulus, and I need something called a fracture surface energy to determine the size of my flaw. And that's under a criteria called a Griffith flaw criteria, which we're going to talk about. But in this ceramic world, we have this argument about flaws that is misguided, and I will show you that. We find in porcelains, everyone says in porcelain, oh, quartz controls the strength, but I find that my strength, okay, suggests quartz particles that are 3 to 10 times larger than they actually are, suggesting a cluster. And in alumina, it's 10 to 50 times larger than the grain size, and I will show you data to back that up. So what we get out of this is that processing determines the strength. Okay, processing becomes critical. So on the left here, I have a cartoon that came out of the literature, and I don't remember where actually. You have a fully dense, perfect, we'll call this a perfect microstructure. Okay. Okay. And then you have one that has some defects, and you can see the defects in here. And these are defects that are pores. Okay. This is a pore here. These are also pores. Okay. These pores that are inside the grains tend to be unimportant. The ones in the grain boundaries, okay, which I'll make purple or whatever. These grain boundary pores are more important in terms of strength control. I can have a microstructure where I have large pores, okay, that are stuck in the middle, or a second phase in the system. And then I have very large pores that are several grains large, that are basically big holes in the system. To give you an example, ceramic microstructure on the right, okay, and these pores here that you see that are kind of triangular shaped, okay, right, like this, these pores tend to be potentially a problem. Here's one, for example, okay. Now in this image, this is a 5 micron size bar down here at the bottom, and this then, the yellow circle here, represents a human hair. It turns out that almost everybody's hair is the same diameter, about 60 microns. It turns out that it's about 60 microns whether you have a lot of hair or no hair. So hair is about 60 microns. It gives you a context for size. And you can see this is a fine grained microstructure, but there are elongated grains. You know, for example, here we have an elongated grain, okay? And then I have equiax grains in here as well, okay? I like those. But I have defects that show up in this microstructure. Now, these are really small defects. So if I were to test this microstructure, I would likely get a high strength. But a friend of mine at Oak Ridge is Andy Wurzak, Annie Wurzak sent me this data many years ago. And this is a size indication here. It's a bin size, so he grouped things by size on a log scale. So this is 1.0, this is 10, this is 100, okay, here at this mark, right? So he measured the grain size distribution in about something like 400 to 500 grains. And then he calculated the flaw size distribution based on the strength data. And what I'm showing you is that the argument was that this, the largest grain in the system, which in one system might be this, which is a very few grains, dictates the strength, but he finds that's not true. And if I take the average here of strength, which I'll say is here, okay, in the middle, and I look at the average over here, okay, my difference here is about a factor of 30 to 50x. Okay, that's a huge difference. It says that the flaws that are in the system, okay, the flaws in the system, these are caused by agglomerates. Or something else like an inclusion, meaning a second phase in the system, okay. But agglomerates in a fine-grained system and in a technical ceramics are more common than inclusions. Inclusions, things that got into the system that didn't belong there. Things that fall off process equipment and end up in the system don't belong there, and that's called tramp iron or whatever. But this data is really telling, but it's also interesting because at the same time that Andy was generating this data, we were generating our own data, and this was one of my thesis students from 2013. There's a lot going on in this slide, but here's your average measured grain size for a series of samples. Okay, so this is average grain size, 0.1 to 10 out here, okay? And there are different temperatures. There were two bodies evaluated, and these are the two different temperatures, or three different temperatures. 1550, 1650, and 1750. So you can see that here, okay, this is the measured grain sizes on average is here, okay? And this is showing us that as I go up in temperature, okay, as I increase my temperature, I increase the size of the grains. Not a surprise, okay? But when I look at this, the largest measured grain is here, and then this set of data shows that this is my range of grain size. But if I were to look at it this way, so I get size versus frequency, and much like I have over here, okay, I would have this distribution, which we would argue is log normal. This is my average, okay, so this point here translates to this line, and this point here translates to that line. Okay, so that's the width of my distribution. So you would assume there's also one down here, which is the minimum grain size. But notice when they looked at their calculated flaw population, this is based on strength measurement. Okay, the flaw populations in this system all sit here. So they are narrowly distributed, but they are, eventually they overlap, but they are constant in this system. In other words, my flaw population at 1550 is about the same as my flaw population at 1750. So there's no real change in the size of my flaw with increasing temperature. That's really important, and we're going to come back to that. When they did fractography on the samples, these were the flaws that they found. So notice that the calculated flaw size distribution and the measured from fractography is a huge difference, but it's also this measured flaw from fractography also is constant, independent of the temperature that was done, independent of the average measured grain size. And so this is telling me that these are defects. These are the defects that are in the system. Now, why is my calculated flaw population different than my measured from fractography? We'll get into that to a certain extent. I don't know whether the American Ceramic Society this year is supporting a fractography short course, but I am an immense fan of fractography, and if you get the opportunity to take that short course, I think that you should. Okay. So we do mechanical testing on ceramics, and I'm going to start up here in the corner. Uniaxial compression, okay? This is also called a compression test, okay? And this is favored by DOT, Department of Transportation. It's done for concretes. And I'm convinced that it's done for a couple of reasons. One is it's a simple geometry, okay? This is simple geometry. The other thing is the strengths are high, very high. And the reason that they're high is because of the geometry of the sample. Then diametral compression, you turn the cylinder on its edge and you do the test and it works great. In this case, by the way, the height to the diameter, it has to be h divided by d is at least 1.0. Okay, so if you took this diametric compression sample here and you measure it this direction in compression as you would for uniaxial, you get unreasonable values and difficult to reproduce. So these are simple tests. In mechanical testing of ceramics, we do flexure testing. And so, this is 3-point here, okay? And 3-point bending versus 4-point bending, okay? So 3 is here and 4 is here. And so what I'm going to do is show you a few more things here in this test. So if I do 3-point bending, I have this situation, support, a support, and a support, and I press on the sample. Okay, whereas 4-point bending does this, of course. Okay, and there's a specification, ASTM 1161 is the specification for flexure testing. Okay, this used to be called modulus of rupture. Okay, and it was designed to get around an interesting problem, and that is tension. So in this bar, if I look at this bar like this, and I've got my support down here, and my support here, and my support here. And by the way, this distance here should be 8 times D, a minimum of 8 times D, okay? So, and this is then D, depth. If you have less than that, if you're less than 8 times D, okay, you have a problem and you get what's called a short beam shear test. So it must be at least 8 times D. Okay, 8 times D is the length of this span on the lower limit. What you get in this specimen is a neutral axis down the center. Okay, so this side is tension, this side is compression. So what that means is in my specimen, my greatest tension is down here along this axis, and I get 0 tension in here. So I have small tension in here. Okay, as I go up, you could argue it's going to be some essentially a triangle. Okay, if my flaw ends up here, my specimen fails at a lower load. If my flaw ends up here, and this one is not existing, this second flaw fails at a higher load, and this one, even for the same flaw size, and this will fail at a much higher load. So in fact, this would require a different flaw to fail. So where my flaw is located dictates then the strength. The closer to this surface, the lower the strength, which is why in Anna's data back here, her measured fractography was much greater here than her calculated flaw populations because of where that flaw occurred on the test specimen. Okay, so what this does and what the equations do is they calculate the strain at this location. Okay, and then they use that from the moment calculation to get a stress. Okay, so we're going to talk about that a little bit. I'm going to make one other comment. Oh, by the way, in my cylinder for compression testing, the reason the strengths are so high is because when I press like this on the system, okay, I end up with a Poisson's ratio effect. This side wants to go out, that side wants to go out, and in the center here, I create a tensile force in the center, and my failure initiates in the center. So it takes a lot of load to get this to fail, okay? So that's why we like this test for concrete specimens. This 8 over D thing, that also applies. D now, okay? D should be a minimum of at least greater than or equal to 10 times the largest feature size. Meaning that if I have an aggregate in the system, okay, my D has to be at least 10x this value. Even better, it should be 30 to 50x, meaning that if I have a defect, if I have a feature size, an aggregate in the system, for example, in a concrete specimen, I may have to have, let's say I had a 1/4 inch, okay? If I had a 1/4 inch feature, 0.25, that means that my specimen now has to be 2.5 inches thick, right? And if I do 8 times 2.5, I end up with 20 inch is my span, L. This is L. Okay, 20 is L. So you see suddenly what I've got is I've got to have really big specimens with large spans in order to test something with a large feature size. So, but we really want that to be 30 to 50x. So for our advanced ceramics and other materials, porcelains, we're nowhere close to, we're way above that value. My biggest defect, our biggest feature size might be 30 microns. So I'm well in the clear with several millimeter sample. All right. I mentioned tensile testing here just briefly. It says direct tensile testing is extremely difficult because what happens in direct tensile testing is that the grips, how I grip my sample, the failure occurs at the grip, not in where you want it to occur. So Griffith, 1920, came up with this equation. The failure strength of the system, okay, is here, is equal to 2 times the elastic modulus times the fracture surface energy, okay? And it's a 2 here because I create 2 new fracture surfaces when the piece breaks. And then pi times c, this has to do with the geometry of the flaw, which we are going to ignore for today, okay? So what I get is 2 times elastic modulus times fracture surface energy is pi c, okay? So let's go into this in terms of what's really going on. I have Hooke's law, 1660. What he says is stress goes with strain. So when I load a sample, I'm straining it. When I take my bend bar and I bend it, let's just bend it this way, this elongates. So my bar bends, and when my bar bends, basically, I do this, right? And the bottom surface then elongates. It doesn't elongate by the amount that the bar has bent this way. It doesn't elongate. It's not this. It is this change in dimension that occurs by this extension. That's my strain. So what I get is if I take, say, a simple cartoon value of this and I pull on it, okay, what happens is it elongates. I'll change my color. Okay, it elongates like this, right? And that elongation, okay, is strain. The amount of force I have to put on here, force divided by area is my stress, okay? So if I pull on this, I pull on it with a load called P, my sample elongates, it contracts in the middle, right? And that gives me what's called a Poisson's ratio. Is the ratio of how much it contracts to how much it elongates, basically, okay? So what I get here is that in a perfectly brittle material, my stress goes linearly with strain until I get to a strain limit, strain at failure, and I get a stress at failure, okay? The slope of this line is the elastic modulus. It's also sometimes called Young's modulus. Okay, after a guy named Young, all right? So what happens is that when I hit my strain limit, this is then a strain limit, the sample fails catastrophically. We tend to think of this improperly. We tend to think of it in terms of strength, but we should be thinking about it in terms of strain. We should think about strain. Because if we think about strain, we learn a lot more about the material. If I have a polymer in the system, I'm going to draw it over here. Okay. I have my strain here and my stress here. If I have a polymer in the system, there's my elastic modulus. Okay. I get my metals in here. Okay. And I get my ceramics up here. So ceramics have a much higher elastic modulus than polymers do, or metals. Okay. So my elastic modulus of ceramics is greater than the elastic modulus of metals is greater than the elastic modulus of polymers. Okay. Now, we have an interesting situation. If I look at elastic modulus as a function of density, okay, what I find is that it scales linearly. Now, if I get to my peak density, right, this is my density max. So fully dense ceramics, for example, this is my elastic modulus max. This is just the elastic modulus of the material. Here's the problem. People like to take this value and apply it, ignoring the change in density. So if I sinter the material, I may start down here, okay? This is my dry ceramic component. Oh, look, at that density, so this is all then densification. Okay, but I have a low elastic modulus down here. All right, that's fine. So what happens is as I densify the sample, elastic modulus goes up, and it goes up linearly. Now, we've done some measurements, and I'm going to show you some data for that here. Okay, we developed some techniques for measuring fracture surface energy. So recall that I have this relationship. Strength is equal to 2 elastic modulus times fracture surface energy over pi c, all under the square root sign. Okay, but what I find is that my fracture surface energy scales linearly with elastic modulus in a brittle material. Okay, so if it's brittle material, or is called behaves elastically, when I stress it, it deforms a certain amount based on the load that's involved. And when I release that load, it goes back to its normal position. So if I go back to here, okay, if I load to this point, for example, so it goes up this path and I'm applying strain to the system and it comes back, okay, to give me a stress value necessary to do that. If I load it this way on the way up, okay, if I stop loading at this point and unload, it follows this curve directly back down to the to zero. So it's elastically behaving. I can deform it and it comes back to where it started before. Okay. Now, this data here, we measured a bunch of different samples, and we found that the elastic modulus appears to linearly track with the bonding. This is actually got evaluated or missed someplace. This is elastic modulus, okay, and this is fracture surface energy, and we have a linear relationship of those two for all of these samples, which are all silicate bonded alumina in some fashion. This is alumina up here, this is silica down here, and they turn out to be on the same path. So that's led us to the conclusion that my fracture surface area change scales linearly with elastic modulus. So I get a slope here, which we call B. So if that's the case, right, and what I could do is come in here and say sigma now is equal to 2 BE times E, because I've got gamma is equal to B times E, okay, divided by pi c under the square root. Now what happens is that strength is equal to E, because I take my E squared out, times the square root of 2B over pi c. Why do you care? Well, if I end up with a situation like this, where sigma strength versus elastic modulus gives me a linear relationship, okay, the slope of this line is the square root of 2B over pi c. Okay. Oh, no, wait a minute. If I go back to the previous slide here, okay, or if you go back to here like this, I've got my strain, my stress. Go back to here. So stress strain, elastic modulus, right? If I do this equation, I get sigma is equal to E times strain. So now strain at failure is equal to 2B pi C if my strength value scales with elastic modulus, which also scales with density. This means that I have one flaw population in my system if my strength scales with elastic modulus, okay, in the system. So we tested that idea, okay, and we came up with samples from industry. And what we find is that elastic modulus, here, strength versus elastic modulus, this is strength over here. And I get a series of curves. This is probably, there's a series of them in here. And the lines represent flaws. So as I go this direction, my flaw size is decreasing, okay? And you can see here's a group, okay, that has a change in elastic modulus. As I go from bottom left to upper right, I am increasing my density, because I'm also increasing my elastic modulus. This is data for alumina, and there were two different alumina samples here. I've got blue and white. They were two different samples as all. And you can see that they scale, and there is a small change in flaw size from 75 microns, roughly. It's not 75 microns, but it goes to 50 microns with densification, okay? So I get a small improvement in flaw size, decrease in flaw size with densification, all right? So the assumption, though, that has pervaded the ceramic industry for decades is that low density strength is due to a connected porosity, that the flaw size decreases with densification. So that porosity is controlling my flaw size, okay? But the thing is that if I measure the elastic modulus as a function of densification and I measure my strength, how are they related? And because elastic modulus is dependent on porosity, there's a rule of mixtures relationship, which we're not going to go into today. Okay, as I densify the system, my elastic modulus increases. If that happens, right, I shouldn't be using the elastic modulus, which I had mentioned before, right? Strength, and I have this relationship, and I have this elastic modulus, right? I shouldn't be using this elastic modulus value. It should be this one, rho versus elastic modulus. And when I'm at my peak density, I shouldn't be using that value. I should be measuring the elastic modulus as I go along in my system. So I need to measure the strength and the elastic modulus as a function of densification. And all these things are linear proportion. Then with that linearly proportional, that means that the strength limiting defect is a constant during my system. So that means that my strength is dictated by the flaws intrinsic to the system when I started. I show you this data for porcelains. We've generated a huge amount of data for porcelains and for aluminas and zirconias and what have you. But the red dots here are the sintering shrinkage is here. This value, this is where we started in the system. It's corrected for that. So this is my dry pieces, but they started off at a smaller end, and then this is my overall shrinkage. So this level here is my sintering shrinkage. And then I come up and I go through a peak. It's actually parabolic. You can describe it pretty well with a parabola. And I get a peak up here. This is my firing range for porcelains, at least for this porcelain, okay? And then if I overfire, what happens is my density decreases because of bloating. So if I looked at this, I say, look, these are dried. No change in, I would expect that as I start to heat treat this, I degrade my network. I would expect my strength to decrease and then my strength to increase as I start densifying. So I would expect sigma to increase here, to be a constant here, okay? And I would expect it to be minimum, go through a minimum down here. So I had a student, Cecilia McGee, she was at Corning. She was fantastic as a student. I proposed this question in class one day, and she took it on as a senior thesis student. So she looked at elastic modulus here as a function of bulk density for porcelains. So this is actually green. And if we were, if the literature was correct, we would expect the strength to decrease when I burn out the clays, which is about 600 degrees C. Okay. I would expect a decrease in strength. And we didn't see that. We didn't see a decrease in elastic modulus. Elastic modulus scaled linearly with density. And then in aluminum oxide samples done by two of my senior thesis students in 20-something or other, 2011, they found the same thing, that here's where you start roughly, it's actually a little bit lower than that. And then their elastic modulus scales linearly with density. That's good, okay? But when Cecilia then went on and she looked at elastic modulus and looked at her strength data, right? Here's sigma again, it's functional elastic modulus. It also is linear, right? Now there's scatter in the data. So one of the things that was remarkable about Cecilia's work is this is all of the data, not just averages and standard deviations. So you see all the data points and it scales linearly with elastic modulus. This slope equates to the strain at failure, okay? And that equates to sigma sub f is equal to 2b over pi c of the square root. And that means that this is constant. So my flaw size, c, is constant because b is constant, 2 is constant, pi is constant. So my failure strain is inversely related to flaw size, and it's a constant. Same here, okay? Failure strain is a function of 1 over c, and it's a constant. What does that mean? That means that my flaws do not change with densification, okay? And so that argument that flaws do not change with densification is a huge deal, because that means that the flaws that we are dealing with in the system are the flaws that we introduced in the process, and that sintering does not eliminate those flaws. All sintering does is it improves my elastic modulus. And by improving my elastic modulus, when I go back to Griffith's equation, sigma is equal to 2 elastic modulus times fracture surface energy divided by pi c over under the square root. If this is all constant, if 2 gamma over pi c is constant, right? I increase my strength, sigma then scales as a function of elastic modulus. It is no longer a function of flaw size. Well, you say, wait a minute, then I don't have to worry about my process. If it's only a functional elastic modulus, I just have to do that. Well, perhaps, but you do, of course. So this is data from Victor Insulator from several years ago. We actually started an experiment of aging porcelains, electrical porcelains. And they have a quartz porcelain that goes through the process, and they have aluminum porcelain. So the aluminum porcelain is higher strength. So if you go in here and you go to 0 and you look at the strength, okay, this is right about 120 megapascals. And you go in here and you look at 0 and you look at the strength. This is somewhere right around about 68 megapascals, okay? So you would come back and say right away, oh, the aluminum porcelain is stronger. And I would say you are correct, okay? So the strength of the aluminum porcelain is greater than the strength of the silica porcelain, or the quartz porcelain. So I can make a quartz here, okay? Great. Okay, we knew that. Why? Because elastic modulus follows the rule of mixtures, okay? Rule of mixtures. And alumina has elastic modulus of alumina is about 400 gigapascals. Elastic modulus of my silica porcelain, if you will, glass, is about 70 gigapascals. So as soon as I start adding alumina in, I increase my elastic modulus substantially. So correspondingly, elastic modulus of alumina is greater than the elastic modulus of my quartz porcelain. So, well, obviously, you know, and that makes sense. So I get a stronger sample. So then, though, when you look at the calculated critical flaw sizes, the maximum critical flaw size for a quartz porcelain is 59 microns. The maximum for aluminum is 63 microns. The minimum is 40 versus 37. These two samples have exactly the same flaw population. I can spell that. Okay, these two samples have exactly the same flaw population. What does that mean? Okay, same flaw population. All right, this means that they're processed in the same factory. That factory has an intrinsic, if you will, flaw population. If I go to another manufacturer, I may find that their flaw population could be smaller or larger than this, right? But the fact is that I have a much stronger aluminum porcelain here, okay, but it has the same flaw population. So that improvement in strength is only due to the elastic modulus, not to a change in how that material was produced. So the hypothesis here that comes back, and by the way, the same thing is true here. I've got two aluminum oxide samples, okay, and they have the same flaw populations. Okay, they had I don't remember which was which. I can predict it here. The white here was what they called their high strength, right? And the blue was normal. Okay. Now they're processed the same way. They're different compositions, slightly different compositions. And if you come out here, you'll see why. Here's my blue strength. Here's my white strength. So the white strength is slightly stronger than the blue strength by maybe 20 megapascals. Not a big difference. But the flaw populations for these two materials processed in the same plant, I'm not going to tell you where, in the same plant, they have the same flaw populations, right? So what does that mean? That means, right, that manufacturing defects are linked to the manufacturing process. So I would argue that no matter what is made in a given factory following the same process, all of those materials are likely to have the same flaw populations. So the only way to improve the strength of the system, and I'm not saying that it needs to be improved, is to then somehow figure out where those flaws come from and then eliminate the flaws in the process. Okay. Is that necessary? Good question. So strength scales, linear elastic modulus throughout densification. This is a huge observation, okay? Throughout densification, because it says that my flaws then are intrinsic and are artifacts of the mixing process or the process itself. In other words, in a given factory, I have the same flaw population for my material going through. Now, we would propose, based on work that we've done subsequent to this, that those flaws are particle agglomerates, okay? They're almost never inclusions, but they could be particle agglomerates. In other words, clusters of material that come in with raw materials that can need to be eliminated in the process in some form, okay? This is important because it says that, and by the way, I didn't go through this slide very well, but I will in a minute. It says that if our process is in control, we will always have the same flaw population. These plots here are Weibull plots. Okay, they're actually called two-parameter Weibull plots of the data. Okay, and I want to show you a couple things that I glossed over that I sort of ignored. There's 4 sets of data here. There's roughly 100 test specimens in general. And what you see is that the quartz porcelain has a single slope. Okay. The alumina porcelain and they're slightly different because of the slopes of these are slightly different because they ignore this. This one has a second flaw population. This is a manufacturing defect that is introduced in some portion of the process. This one doesn't have it. The quartz porcelains all have a single slope, so there's one flaw population that's incorporated in all. This has what's called an exclusive flaw population here, which we may get time to talk about tomorrow or Thursday, saying that this is where there's a potential for process control improvement. Up here, we're fine. And in fact, these two lines, they don't appear to be the same slope in this plot, but that's because of the x-axis. These are the same slope. So essentially, we have the tools to figure out what's happening in our process, and that comes back to why we generate mechanical testing data and how we use that data in general. So I would like to point out that I'm remarkably close on my time, okay? So if I were to go back and just summarize ceramics versus other materials, Ceramics have very high melting points. They are good electrical insulators. They are good thermal insulators. Okay. They're typically optically translucent, and I just sort of glossed over this as not particularly important to what we're talking about, but metals are opaque. Ceramics are typically translucent or can be. Very high strength, very high elastic modulus, right? But very low toughness, so they are brittle. The exceptions to this in terms of toughness are only two, okay? And the two exceptions to this are partially stabilized zirconia or yttria stabilized zirconia, okay? The other is silicon nitride. There are only two materials that have been developed in the 100 years of investigating, 100 plus years of investigating ceramic materials that have high toughness. Everything else is brittle, and there are just no exceptions. And the fracture toughness values are very low. We tend to be abrasion resistant because we are hard and resist damage and last low thermal expansion coefficient. Okay, so that takes care of it for me. What we do tomorrow is session 2. I'd like to talk about ceramic forming processes and cracking and warping. Okay, because I do not like attributing cracking and warping to the drying and firing processes. And then powder characterization, and I'm shooting for thermal processes tomorrow. Things like drying, calcination, pyrolysis, sintering, etc. Possibly we'll get to that tomorrow. So I think where I'm at the moment, let me see if there are, I'm going to stop sharing. And there's one comment. There's fractography short course in person at the American Ceramic Society spring meeting in 2026 in Bellevue, Washington. And there's also short courses offered during the regular year. One last thing, I'll put it in the chat. You can work through the American Ceramic Society. You can email me questions if you want, or you can bring them to class tomorrow. Questions for me? Good.
I'm sure I'll have questions tomorrow. I think so.
Great. So have a great day. We'll see you tomorrow morning.